Hello, geometry students. Appreciate you finding time to do your notes. These are the notes for Wednesday, the 13th, November the 13th class, and we're going to be continuing our discussions on similarity by taking a look at scale factor. So let's get to it. Our objective will be the student will strengthen their knowledge of scale factor and learn to apply it to similar polygons. Again, the date for these notes is Wednesday, November the 13th. Copy down your objective and your date. Anytime you need more time, just press pause and then press play when you're ready to move on. Now, scale factor sounds like something that is familiar to you. Well, it should. This is something that we talked about earlier this year, and we talked about it doing dilations. And as we well know, dilations is when we change an object's size. Well, similar polygons is basically the same idea. We're going to be changing objects' sizes. Okay. Now, we have been talking about similar figures. In our efforts to determine if figures are similar or not, we have been setting up proportions to check to see if corresponding sides are in proportion or not, because that's one of the main qualifications for being similar, is that corresponding side lengths have to be in proportion to each other. Now, we developed a basic strategy for filling in the proportions where we took the numerator from one ratio in the proportion. We got the numerator from one figure, and then the denominator would be the corresponding part from the other figure. So in each ratio you had one value from one figure and one from the other, and then we did that with all of the ratios while we set up our proportions. So we repeated the same idea for the C and the D in the ratio. Then, in order to determine if we had a good proportion or to solve for a missing value in our proportion, we cross-multiplied within the proportion and solved to see if either the proportion was balanced or to solve for the missing piece of information. But there's a little bit deeper connection going on inside of these proportions that we have not yet looked at. That's going to be the focus for today. Okay, now yesterday we started off with an example that looked like these two triangles. Okay, so you don't necessarily have to copy this top part down. I'll tell you when to start copying again. Okay, so the example we started with had this red triangle and had this blue triangle, and we set up proportions to check to see if we could have similarity. And in the proportion on the left-hand side there, you got 4 to 6. Those were the smallest sizes. Smallest sides of the two figures, and we allowed that to be equal to the 6 to 9, which was the medium side lengths of the two figures. And then the next one, 6 to 9, was the medium side lengths, and we let that be equal to a ratio containing the largest side lengths, 11 to 16.5. And then, of course, the largest side lengths and were compared to the smallest side lengths on the last proportion over there on the right. In the end, we used three ratios over and over and over again. They are, of course, the small side lengths, 4 to 6, the medium side lengths, 6 to 9, and the 11 to 16.5 was the largest side lengths. Now, when you take a look at those ratios, obviously they look different from each other, but all of these ratios have something in common with each other. Each of them can be reduced. Okay, so let's see what happens when we reduce these ratios. Okay, so start copying again here. We've got 4 to 6, we've got 6 to 9, and we've got 11 to 16.5. Okay, now if you think about 4 and 6 on that first ratio, is there a value that will get into both the 4 and the 6 at the same time? Sure, those are both factors of 2. We could divide a 2 out of each of those values in order to reduce it. The ratio in the middle, a 6 to 9. Do a 6 and a 9 have a factor in common? Well, sure they do. They have a 3, so we could divide a 3 out of each of those. Now, the final ratio over there is a little bit harder to detect, okay, because we have a decimal point in there. Okay, but these values will also reduce as well. Okay, an 11 and a 16.5 do actually have a value in common. 5.5 can divide into both of those. Now, typically, we don't divide in decimal numbers while we're trying to reduce a fraction or anything like that, but since this problem already had decimals in it, then it's not making it any more complicated to divide it by decimal points. Okay, so 2 can reduce the 4/6 ratio, 3 can reduce the 6/9 ratio, and 5.5 can reduce the 11 to 16.5 ratio. So that's what we're going to do. We're actually going to reduce these by the values that we have determined. And the resulting ratios coming out of these three reductions is what is so interesting. Clearly, all of the ratios have come out the same. Now, this is going to be a truthful situation if you are dealing with similar polygons. Okay, so this is actually another check to see if you have polygons that are similar or not. Okay, if we would have come out with any ratio that was different amongst these three, then that would probably mean that the polygons were not similar to begin with. Okay, and this common ratio, when you take these, take the ratios of the side lengths like we did at the top of the screen, and we reduce them down to their simplest terms, where we get to prime numbers and they cannot reduce any further, then this ratio is actually the scale factor that controls the side lengths between the two polygons. And again, you may recall scale factor because it told us on a dilation how much bigger one figure is going to be from the other, okay, and also whether it is going to enlarge from one figure to the other or whether it is going to shrink from one figure to the other. Okay, so we have a 2 to 3 scale factor on this picture, meaning the left hand, since the numerator is smaller than the denominator, the left figure got bigger, becoming the right figure, and it was a 2 to 3 ratio that it grew by. Okay, so let's take a look at another example. Okay, if the following two triangles are similar, what is the scale factor? So we have two triangles here, and there's a lot of information in there, so get that copied down. And while you're copying it down, I want you to consider this note. Okay, some people may be wondering, you know, how on earth did I reduce that last ratio on the last example? I would have never seen that 5.5 would have divided into both of those numbers, and that's fine. That's understandable. I don't expect you to have division by decimal points memorized or anything like that. Okay, so if you run into decimal points like we did on the last example and like we will on this example, there's nothing wrong with going to your calculator to figure out how a fraction is going to reduce or things like that. Okay. Now, what we need to do is we need to figure out the scale factor. That means we're going to have to set up the ratios that go from one figure to the other. Okay, so just like we did last time, we are going to compare from left to right as we move from numerator to denominator in each ratio. And I'm going to follow the same strategy that I gave you last time. I'm going to pick on the smallest set of sides first, then the medium-sized sides, and then the largest sides. Okay, so my first ratio is going to be from the smallest sides from the red triangle to the blue triangle. So obviously the first ratio is going to be the 3 from the left triangle, and it will be to the 3.6 from the right triangle. So 3 to 3.6 is going to be one of the ratios. The medium-sized side lengths would be the 4 from the left and the 4.8 from the right. And the largest ratio will be the 5 from the left and the 6 from the right. Okay, so setting up those proportions, I'm going to go small to medium, medium to large, and large to small. Okay, so there are the three proportions that would be in play here. We can double check to see if these following these two triangles are similar or not by cross multiplying and seeing if the proportions are balanced or not. Okay, in the proportion on the left, 3 times 4.8 is going to be 14.4. And the 4 times the 3.6 is also 14.4. So that is a good proportion. In the center, okay, 4 times 6 is 24. And 5 times 4.8 is also 24. So that is a good proportion. On the right, the 5 times 3.6 is 18. And the 3 times the 6 is also 18. So what we have here is we have 3 good proportions. That means our triangles are similar. Okay. Now what we can do is we're going to have a look at our 3 different ratios. Okay, and they are the ones that are on the left side of each of our proportions, the 3 over 3.6, the 4 over 4.8, and the 5 over 6. And we're going to see what it might involve to reduce one of these fractions, one of these ratios, into its simplest form, because we know its simplest form is the scale factor that controls this problem. Okay, now just having a look at the ratios, okay, a ratio in its simplest form will not contain a decimal point. It will reduce or possibly even enlarge in such a way that it will get a whole number for both the numerator and the denominator. Okay, so I'd like to consider the largest ratio that we have on this problem is the 5 over 6. Okay, those are both whole numbers, and a 5 in the numerator and a 6 in the denominator. Can that ratio be reduced any further and still have whole numbers for both its numerator and its denominator? I don't think it can. There's no whole number that'll go into a 5 and a 6 at the same time. So 5 over 6 is going to be the scale factor that controls this problem. Okay. Now, one of the things that the scale factor can be used for is to help us find missing side links if we already know that 2 figures are going to be similar. Okay, so just like yesterday, sometimes we have proportions that are all filled in, and sometimes we have proportions that are missing a side length. The math remains the same. We just have to work the problem out. Okay, so the ratio of the scale factor can also be used in proportions to help us find missing side lengths. So this example says that the following 2 pentagons are similar. If the scale factor between them is 1 to 4, find the missing side lengths. Okay. Now, obviously, we have the 2 pentagons there. Okay. The smaller of the 2 is has all of its side lengths marked in there. Now, we know that is the smaller of the 2, not because it is drawn smaller, but because of the ratio. See, the ratio on the scale factor reads 1 to 4. That's a smaller value becoming a larger value. So we know it's going to be an enlargement. Okay. Now, we need to set up proportions that can utilize or set up proportions that can help us figure out what side lengths are missing from the large pentagon over there. Okay, but when we go to set up a proportion, okay, we need more information to help set us up. Okay, we need 2 fractions to set up a proportion, and seemingly we only have 1 from the small pentagon to the large pentagon. Okay, with the large pentagon's values being completely missing. Okay, but once you know for a fact what the scale factor is, that ratio can be used to help you figure this out. Okay, now you are going to be figuring out the values, the missing side lengths of the pentagon. Okay, and you're going to set up a proportion for each missing side length. Okay, now I gave you a hint here. We're going to use the scale factor. Okay, from the left figure to the right figure, the scale factor is 1 to 4, just like is written on the screen. Now you need to set up the other side of the proportion. Okay, numerator should be one of the side lengths from the small pentagon, and the denominator should be one of the side lengths, or the corresponding side length, from the larger pentagon. Okay, So you're going to set it up, filling in the missing side links into the proportion, and then you are going to have to do that 5 times once for each of the 5 missing sides. Okay, so have a look at this. Let's see if we can figure out the 5 missing side links, and we will have a look at them together once we get back in class on Wednesday. But give it a try there on your paper. I appreciate you finding time to get your notes done. I'll see you in class on Wednesday.